I'm with Thomas Schulthess, director of the Swiss National Supercomputing Center, also known as CSCS, and professor of computational physics at ETH Zurich. Thomas, tell me about your career and how it led to to working with supercomputers, and eventually to your becoming director of CSCS.
Yeah, thank you, Pat, for having me here. Yes, I started my career working on magneto-electronic devices, or spintronics, as it was called under the DARPA program that supported my research then. Around 2003, when Oak Ridge National Lab seized the opportunity to propose the Leadership Computing Facility as the US response to Japan's Earth simulator, my focus shifted to extreme scale simulations of strongly correlated quantum systems. That transition increasingly drew me into the field of supercomputing. In 2008, though, through a series of coincidences, probably orchestrated by former ETH colleagues, I found myself negotiating for my current position. Returning to Europe was not really my plan, but I'm here now, so things happen.
Right. Okay. And tell me a little bit about your interest in, I know that now you're the director of the lab, so maybe you're doing less research, but can you tell me something about your interest in physics simulation and the challenges of it, and maybe something about the challenges of multi-physics simulations?
Yeah, okay. So as I mentioned just before, my work at the time was focused on quantum physics. However, when I joined CSCS, my focus began to shift towards weather and climate simulations. This was driven by what initially seemed like unreasonable expectations from Swiss. And thanks to a very remarkable collaboration with engineers from then Cray and NVIDIA, as well as the scientists from ETH Zurich's Environmental Science Department and Swiss, we successfully deployed Swiss's new Cosmo Next model on GPUs in 2016. This achievement improved price performance by an order of magnitude. The collaboration also laid the groundwork for the beginning for bringing the Icon model to GPUs. The GPU-based systems we have today, like Lumi, which is part of this Destination Earth program of the European Commission. It's just unfortunate that we are no longer eligible to participate in those programs, but it's again how life develops. We don't control everything.
Right. Okay. Speaking of not controlling everything, and you talked about quantum physics, Richard Feynman famously said in 1981 that digital systems can only offer approximate simulations and they don't scale well. He said, however, that a quantum computer would be able to perfectly simulate physical reality, which is quantum in nature. What do you think about that? That's a big open question.
Change the subject. So you're referring to the statement whereby nature isn't classical, and if you want to simulate it, you'd better use quantum mechanics.
Right.
So thanks to the theory that Richard Feynman helped formulate, quantum simulations on digital systems today are highly accurate and predictive. Okay? That's a term that he didn't predict like that.
Yeah.
However, scaling these simulations remains a significant challenge, which is where quantum emulators are starting to play a crucial role today. In other domains, that rely on classical simulations, though digital computers will continue to dominate. So, like the weather domain we were talking before, that has other aspects where classical simulations continue to be important.
Okay. All right. So what do you think about the future? We now have sort of a supercomputing paradigm. There are variations. You have the use of GPUs versus CPUs, depending on whether you need floating point or not. But what do you think about the future of the supercomputing paradigm as it is today? And do you think it'll continue to improve, but keep the same sort of approach? Or do you think an entirely different approach is necessary?
Okay, so going back a bit, we're working on this infrastructure we call Alps. And so it was scientific computing that motivated the development of digital computers and high-performance computing. And so supercomputers are simply the most powerful general-purpose high-performance computing system in their time. That was in the past, and that is today. And also science, and I'm convinced of that, will continue to play a pivotal role in our global cultures, and so will supercomputing with it. What evolves is the way supercomputers are implemented, a transformation that is constant and ongoing. This has been the norm for decades. What would have, for example, you just mentioned it, GPUs. Who would have imagined a decade ago that GPUs would become so dominant in supercomputing?
Right.
And I've gone through this history. I can tell you, nobody. Okay. I'm confident that the cloud-native approach we've adopted on Alps will gain traction elsewhere, as it enables scientists to handle complex data-driven workflows in their respective fields. For instance, Isambard AI, currently being deployed in Bristol in the UK, uses the exact same system architecture as Alps. Jupyter, UHPC's first exaflop machine by traditional metrics, set to begin operation next year, maybe in 9 months from now, is based on the Grace Hopper technology that NVIDIA scaled up with HPE and CSCS on Alps. So the paradigm shift you're seeking is already underway, and it will continue to unfold. That's the essence of science. It drives innovation, transforms society, and while the process is nothing new, it's been going on for centuries, it remains full of surprise.
And by the way, where does the name Alps come from for your supercomputer?
That's a good question. With a few exceptions, CSCS has always named its supercomputers after peaks in the Swiss Alps. Changing that tradition would have been a political suicide for me. Though having been born in Nepal and raised in East Africa, where there are even higher mountains than in the Alps, the temptation was clearly there. The new infrastructure, which we call Alps, is still a supercomputer, but features a cloud-like architecture. It supports multiple software-defined partitions that function as traditional supercomputers for different tenants. We've continued the tradition of naming these partitions after Swiss alpine peaks, and it makes sense to name the underlying infrastructure after the mountain range itself, the Alps. And by the way, specific data infrastructures are named after lakes in the Alps.
Okay, great. Now you said you're from Nepal, and as I understand it, you grew up in East Africa. And I know that you did some mountain climbing. Do you still do that, or what about your outdoor activities?
Yeah, they have changed. So sailing and mountain climbing is what I did before I married. When I met my wife, I had to drop the mountain climbing because she is afraid of heights. And but I continue to exercise outside and I swim in outdoor in open water, and I do that also in the winter.
That's very brave of you. Okay. Okay, Thomas, thank you very much.